Now, our next kind of integral is going to involve decomposition of fractions into, I'm sure you can guess, into smaller partial fractions. And honestly, this is a specialized method which we can preview through these two integrals. Now, I actually kind of have a question for you. Which of these two integrals would you rather do? You can't say neither. Would it be integral A, 4 over x plus 3 over x plus 7, or would it be integral B? Well, really the question more is which one can you do using the methods that we've discussed so far? And the correct answer is A. And the reason that it's A is because both of these fractions are of the form 1 over x. And remember, when you are in the form 1 over x, you can always integrate using an ln. So both of these can be integrated, again, using the concept of ln. Now, the interesting thing here is that option B is actually going to be the same answer. And that's because both of these are actually the same, both these fractions are actually equal. And what we're going to learn today is how to take this complicated fraction, this choice B fraction, and actually turn it into these smaller partial fractions. And when we turn them into these partial fractions, as you already saw, we can actually integrate, often with ln or something basic. The real part of today's lesson is going to be learning how to do the algebra that decomposes this big fraction into the smaller partial fractions. Now, some of you might remember this method from last year. It depends on your trig class, but even if you don't remember it or never saw it last year, never fear, I'm going to be going back through the algebra today. But again, once we get through the algebra, the calculus is easy because you'll have these smaller partial fractions that enable you to use basic integration. Now, if we want to integrate x plus 4 divided by x squared minus 5x plus 6, we definitely do not want to try to use ln's because it's not of the form 1 over x. We're not going to be able to use inverse tangent, and the honest truth is what we need to do is we need to start to decompose this fraction. Now, the premise on decomposition is that you break the fraction down into its factors, and it looks like that the denominator factors very nicely, which allows us to be confident that we'll be able to split this into two fractions, each containing one of these denominators. Now, as you can see, the numerator is yet to be determined. The numerator is unknown, so we can call it A and we can call it B. By the way, it wouldn't matter what order you put these factors in. It wouldn't matter which ones with A and which ones with B. We're still going to end up with two fractions that are decomposed. Now, our goal is to find A and B, so what we want to do now is we want to start thinking like this is algebra, and what that means is we're going to want to multiply both sides of this equation by the LCD. Now, the LCD is going to be simple because it's just going to be both denominators, but still we're going to multiply the entire equation by that common denominator. Now, when you multiply, remember that you multiply to the numerators, and also we're going to get a lot of cancellation. In fact, the first cancellation is that the denominator is going to completely cancel with this LCD. That's going to leave us with just x plus 4. Our next cancellation is that the x minus 3's are going to cancel, which is going to leave us with just the x minus 2. And for our last cancellation, the x minus 2's will cancel, but that will leave us with the x minus 3. Now, notice that we're also left with the a and b, which is beside both of those corresponding factors. Now, again, this is still an algebra equation, so we're going to keep thinking algebra. We're going to do the distributive property, kind of separate and split this up a little bit. And I'm also going to organize these terms because I know where I want to go. I'm going to organize the x terms, that is the ax and the bx, and I'm also going to organize the other terms, that is the minus 2a and the minus 3b. We're basically going to put them, the like terms, together. Now, we're getting close, but there's one more kind of preliminary step so that we can solve for a and b. And that is that we're going to want to factor out the x. And if you're saying, well, how am I to know to do that? You'll find out the reason that we're factoring is so we can get ourselves ready for this main step. Now, our main step is to take full advantage of this equal sign. Maybe you've never thought so much about an equal sign as you did today, because if both sides of these equations are equal, that means the values that are in front of corresponding terms have to be equal. That is, whatever's in front of x on this side of the equation, the number 1, has to equal whatever's in front of x on this side of the equation. That is a plus b. So we can make a real simple statement. We can say that a plus b has to equal 1. That's because of, again, this equal sign. Now, we can also say that the other terms, that is the constant, has to equal whatever is the constants over here. And so 2a minus 3b would have to equal 4. And now we've set up a system. And of course, a system from your algebra days can be solved for, in this case, for a and b. Solving this particular system is probably a matter of just thinking real simple about some opposites, maybe multiply everything by 2 so that my a's can cancel out. That leaves us with negative b equaling 6, which of course means that b equals negative 6. And I can plug that back in as I wish, probably plug it back in for b right here, and be able to determine the other half of your system, that is that a equals 7. Now, the important thing to remember, that is, if a equals 7 and b equals negative 6, that we now are able to say that this original integral can be equal to 7 over x minus 3, I guess really minus 6 over x minus 2. In other words, we can fill back in our values for a and b. But now the power of this entire problem. The power of this problem is that I can actually do the antiderivative of each of these partial fractions, of course, using ln. So my antiderivative, capital F of x, is going to ultimately just be the ln of each of these fractions, with of course the coefficient. But almost too easy, we can do the antiderivative. Don't forget your plus c, but realize that the main premise in this problem is that we split up what was once a complicated fraction into these two partial fractions so that we could do those two antiderivatives. Now, did you remember the method from last year? Some students say yes, they do. Some say no, they don't. But in either case, I would challenge you right now to try to split up this fraction into partial fractions as much as you can on your own. Now, I'll be a couple steps behind you, but I want you to start thinking, well, how could you split up this denominator? How would you factor it? Okay, what you're seeing here is a GCF type factoring. But with the ultimate goal of continuing to split up the trinomial and now ending up with 3 factors. So where will these 3 factors go? Well, they will become the denominators of 3 fractions. Now, usually I help students get to this point, that is to set up the template of a over x, b over x minus 4, and c over x plus 3. But in all seriousness, I challenge you to try to solve this for a, b, and c. Try to go through the steps where you simplify this equation and eventually turn it into a system. I will be a step behind you, but you'll have to push pause to stop, obviously stop the video so that you can think about each step before you see the next step. LCD coming up next. Cancellations coming up next. Organize the terms, do the distributive property, and try to get, actually do the distributive property, multiply out, and then try to organize your like terms. Coming up next. So what I did here was distributed A, B, and C, but I went ahead and just got all the x squareds together. Now I'm going to do the same thing with just the plain x's. Again, I'm going to distribute A, B, and C. Now there is one number that you don't want to lose, and that is when you distribute A onto that negative 12, that it becomes basically its own term that'll be at the end of the equation. Now the next thing we want to do is we want to factor. You're actually going to be factoring something out of each of these three groups, not really, I guess, out of the third group, but you are going to be factoring and sort of organizing one more time. Leave the negative signs on the inside, as they will be part of the A's, B's, and C's. Okay, now we're coming up on that most crucial point. That is the point where you want to equate both sides. To equate both sides is to say that both sides have to be equal. That is, whatever's in front of x squared has to equal whatever's in front of x squared on this side of the equation. Now, there is no x squared on this side of the equation, so what number's in front of x squared? That's correct, 0. So we're able to say that whatever's in front of x squared, that is a plus b plus c, has to equal whatever's in front of x squared on the other side, that is 0. So what's in front of x? Obviously, it's negative a plus 3b minus 4c. But what's in front of x on this side of the equation? Well, of course, there is no x, so once again, 0. Now, our last term here, let's be careful, it's the term that actually is like the constant. And so this whole negative 12a, is equal to whatever's the constant over here. Well, that's the only thing we actually have. That's equal to the number 1. And so now we have ourselves a system. Now, how do you solve this system? How do you solve a system that has 3 variables, a, b, and c? Well, there was a calculator method that we would have done last year in your trig class, and maybe even before that, but it's a nice calculator method. It's a matrix method, and you are able to think of the left side of this system as a 3 by 3 matrix. You're able to think about the right side of this system as a 3 by 1. And the beauty in this method is that all you got to do is pick the coefficients of your variables. So the coefficients of a, b, and c are 1, 1, 1, -1, 3, and -4, and then -12 is the coefficient on a, but zeros are the coefficients on the b and c that do not exist. And we usually call that matrix A, and then we take the constants, that is 0, 0, and 1, and we call that matrix B. Now, what you'd want to be doing right now is you'd want to be remembering how to type this in your calculator. In fact, you should be getting out your graphing calculator and physically typing in each of these matrices into as a matrix A and a matrix B. Now, remember how this works. You want to find the matrix button. You also want to actually slide over to edit so that you can type in these 9 numbers into matrix A. So these 9 numbers, these are the coefficients of A, B, and C. So it's a 1, 1, 1, -1, 3, -4, -12, and then 0 and 0. Now remember, the whole magic to this matrix method is to use the formula A inverse times B. A inverse times B is actually going to solve that matrix, solve those 2 matrices to give us the solutions to the system. So you're going to have to get the matrix A symbol on your screen. You're going to have to get this inverse symbol, which is actually just the button x to -1. And then you're going to get the symbol B on your screen. So again, it's A inverse times B. And out pops your 3 answers, which are A, B, and C from the original system. Now, these 3 numbers, they look kind of sloppy. It's nice to turn them into fractions. Using the fraction key that's the fraction operation that's in the math menu, simply select that and it will turn your 3 decimals into the fractions -1/12, 1/28, and 1/21. Now remember, the whole premise of this is that we're trying to find the numerators to these 3 functions, or 3 fractions, and what we need to do now is we need to substitute these in, but ultimately, I'm going to try to do the integral. I'm going to try to do the antiderivative of these 3 functions, or 3 fractions. So you might as well just get right to it and do the antiderivative of each of these, which will be ln's. So we're going to end up with the ln of x, but -1/12 will be the coefficient on that. We're going to end up with the ln of x -4, but 1/28 is going to be the coefficient of that. And we're going to end up one last time here with the ln, but 1/21 is going to be the coefficient of that. Don't forget to plus c, but really we're just doing the antiderivative of each of these 3 fractions, and keep in mind that these 3 values for A, B, and C just became the 3 coefficients of each of these ln's. Now, there's 2 special cases when it comes to performing partial fraction decomposition to be aware of the makeup of the original fraction and how it changes somewhat of the template where we put a over a denominator and b over a denominator. I want to show you both these special cases. The good news is the calculus is still easy. It's really this algebra process of decomposing that, of course, requires most of the work. All right, now if you take this fraction, it doesn't look a whole lot different, but when you investigate the denominator just a little bit more and you think about factoring it, you discover pretty quickly that we have what's known as a repeated factor. When you have a repeated factor when it comes to this partial fraction decomposition, I'm not able to just without any concern, just put each of these x plus 2's in the denominator. Not without thinking a little bit about the idea of the fact that they're repeated. And so the story goes that we have to step up to this degree. Now, we have a degree 2. That means that I have to step through the first degree till I get to the second degree. And so really each denominator kind of builds until I get to the highest degree. I want you to imagine with me that the highest exponent was 3. Well, then I would have to take one more step to get to a degree 3. Of course, that's not the case. We're not going to end up with that. But as many times as it repeats, you have to show each of those denominators so that we can have the proper setup. In this case, a over x plus 2 and b over x plus 2 squared. Now, the good news here is that this actually makes it a little easier to solve this problem because when you start getting into the business of multiplying by the LCD, you find out that the cancellation is pretty nice. Now, make sure you pick the right LCD. The LCD has to be whatever's required to multiply so that I can cancel with both denominators. And that means that I need to have an x plus 2 squared. Not an x plus 2 cubed, but just an x plus 2 squared, because if I put, of course, x plus 2 squared in each of these numerators, well, that's going to cancel enough here. Obviously, it's going to cancel and leave me with an x plus 2, but the next fraction is of course, going to completely cancel. And that's the idea, but that's all that's needed, just an x plus 2 squared. And so in this case, all of it cancels. Now, don't forget about multiplying it over here to the other side, but when you do that, you find out that it also completely cancels, but that leaves us with a 4x. So we have 4x, we have a times x plus 2, and just b. Now, when you go through the steps of solving this equation, remember you're solving it for a and b. So you do want to, as we often do, you want to distribute here so you can start to collect some terms. Really, the only terms that need collected is this 2a and this 1b. They're going to go beside each other. This ax here is what's going to be needed for us to start setting up our system. So the cool thing here is that you already have half of your system solved because you now know that a equals 4. But the other half of the system is the constant, and remember the constant is, in this case, 2a plus b. Well, that would have to equal whatever is the constant on the other side of the equation, which of course is 0. So we have ourselves a system, but again, a already equals 4. Do a little simple math, and we find out that b, of course, has to equal -8. Now, once you get these two answers, a equal 4 and b equal 8, -8, we're able to go back up here, of course, and fill them in, but don't forget that the whole point behind this is that it's now time to do the antiderivative. Now, the antiderivative of 4 over x plus 2, that's going to be another ln, because that's still of the form of 1 over x. In other words, x to the first power. But when we look a little more closely at the second one here, we have to be aware that this is not going to be an ln. The truth is this is going to be a little mini substitution method. The substitution method is going to require us to let u equal the inside so that we end up being able to change this problem into really an 8 over a u squared. Of course, it's really -8, but ultimately here we want to think about how to do the antiderivative of something over x squared. Well, I hope you're thinking of that x squared as a -2. In other words, as a negative exponent. So I have -8, u to the -2. Now I'll be able to add to that exponent and divide by that exponent. Now when you add to a negative exponent of 2, you get a negative exponent of -1. And of course you also have to divide by that exponent. So when it all shakes out, my antiderivative is going to look like a +8 u to the -1. Now u to the -1 is going to end up as a negative exponent flipping back to the bottom. And really, since u is equal to x plus 2, I'll be able to fill that back in for my final answer here. So it's 8, +8 over u, but again, u is x plus 2. Don't forget your plus c. All right, so final antiderivative is 4 ln of x plus 2 plus 8 over x plus 2 plus c. All right, now our final special case here is actually an improper fraction. As you copy this down, take notice that the numerator has a higher degree than the denominator. And whenever you have any kind of fraction where the numerator is larger than the denominator, we call that improper, which really means that there's a whole part of this fraction that needs to be divided out. In fact, that's exactly what we're going to do. We're going to start this improper problem by first dividing it out so that we can start to decompose this. And again, as we set up this long division, keep in mind that the decomposition is first we have to get this whole part out. Now remember how to do long division. You look at these first two terms here. Think about multiplying 2x to x squared so that you can get 2x cubed. You always want to end up with the same thing. You want to end up with the same degree. So I end up with a 2x cubed, and that allows me to begin and continue this process of long division. Now, be careful because you always subtract in this step. As I always tell students, the subtraction needs to distribute. And so a lot of times what students like to do is just distribute the subtraction sign right away. Now, it just, these terms will always cancel because you made them the same. It just so happens that these terms right here cancel because they're the same. That doesn't always happen, but I do end up with a 5x minus 3. Now, the division is over because no longer is my result higher than my denominator. But remember that this 5x minus 3, even though it's a remainder, can be written as being 5x minus 3 over x squared minus 2x minus 3. Now, what's starting to happen here is we're starting out with an improper fraction. We've just decomposed it into a whole number, this 2x, but also into another fraction, this 5x minus 3 over x squared minus 2x minus 3. So guess what we need to do with this? Well, that's right, we need to decompose it. And how do you decompose it? Well, you go through the same process that we've done numerous times. That is, you set up your little template of A over and B over, and start to find A and B. Now, I'm not going to go through all the work here, but I'm going to remind you that you would have to factor the denominators, put them under A and B. Eventually, you go through the process and you would discover that A equals 3 and that B equals 2. But the most important thing is to think about how you're going to integrate, that is, come up with your final answer. So we're going to integrate each one of these. Integrate 2x, yes, that's part of the decomposition. Thankfully, that's easy, and that ends up just being x squared. Integrate your next fraction. It's going to be a nice little ln, so 3 ln of x minus 3. And your last fraction, which is another ln, so 2 ln of x plus 1. So remember, if you have an improper fraction, you always have to divide out the improper part and then decompose the rest. And now you're ready for your exit problem.